Good morning, everybody. Again, welcome to the lecture on that is the pipe flow analysis. So, in this lecture, we focus on the pipe network. Ultimately, whatever you learn in pipe flow analysis is finally in field. You want to implement it. It is with the network analysis. That is pipe network. That means, suppose we are laying a water distribution pipelines in a village or in a municipality. How generally we do? We'll have the overhead tank at the highest level in that village. And at that place, we construct the overhead tank and store the water in that overhead tank by pumping from a reservoir which is nearby. Once water is stored in that reservoir, it will be distributed to the entire village or to the entire locality in a municipality through the pipes. There will be main pipeline, there will be distribution pipelines, there will be sub pipelines, there will be going finally into the house. So if you look at these networks, each pipe diameters are different. The mainline pipe diameter, which brings water to the overhead tank, may be of 1 meter diameter or 50 centimeter diameter. But the water which is taken to, for example, to the entire village, the main pipeline may be of 30 centimeter diameter. From there, the pipeline which goes to the sub pipelines may be of 15 centimeter diameter. From there, the pipeline which goes into again the streets wise maybe of 10 centimeter diameter, and from there to your house it may be of, for example, 2.5 centimeter. So like the different pipeline systems. So that's why my sincere request to you, you please visit any of the what you call it as this pipes shop and inquire what are the various sizes of the pipes that are available. Pipes, you cannot have your own size of pipe. Okay, for doing problem sake, for theory learning, pipe diameter, we can get anything and we write 9 centimeters, 5 centimeters, 4 centimeters, 3 centimeters, 2 centimeters, like that. But are they really available in the market? The market availability will be different. There may be, for example, 2.5 centimeters, 1.25 centimeters. There may be, for example, 5 centimeters. There may be, for example, 7.5 centimeters. There may be, for example, 10 centimeters. There may be, for example, 15 centimeters. So, like that, what are the standard sizes of the pipes? You can go through the YouTube also and then check what are the standard pipe sizes of the pipelines that are being used in a water distribution system. So that gives you an idea about what is happening actually. So in that context, how actually this pipeline network will be a little bit introduction only we are giving at this level, but real analysis I'm not really touching here at all, but that's beyond your level. But you should understand that there is a system of network analysis when we are planning water distribution to a village or to a area or to a municipality or to a town, whatever it is, there is a system actually. It's a that system. What is it? I want to just introduce that so that when once you enter into the field and then you start doing it, you understand how to go about it. Right? With this introduction, I will share the whiteboard and let us discuss in detail. It is an interconnected system of pipes forming several loops. I told what the example is. water distribution system in a municipality, right? So then actually what it is, what we have to find out, we need to determine the distribution of flow in various pipes of the network. This is what our job is, because ultimately anybody, when they are taking a pipe basically into their house, for ultimately what they should get, should get the discharge. So how to distribute the flow in this entire network, that is what our main task is, to find out that actually. In order to really do it, there are certain necessary conditions. There are certain necessary conditions to be satisfied. What are they? Right? Number one, the flow into each junction is equal to the flow out of each junction. The flow into the junction is equal to flow out of the junction. What is this? That's nothing but satisfying continuity equation. That's all. Then next, number two, the algebraic sum of the head losses around each loop is equal to 0. That is second. I will explain by drawing a loop also. Again, we take here actually head loss in clockwise direction. Head loss calculated in pipes in clockwise direction. We take it as positive, anti-clockwise negative to calculate with. Then next, basically, if you take it, head loss in each pipe is given by, for example, HF is equal to some R into Q square. What is this R? Suppose, for example, you take it. You know HF is equal to FLV squared by 2GD. So what I can write, FL into Q square by A square into 2G. So that is equal to FL into Q square by 2G into pi by 4, basically 2GD, sorry, 2GD into pi by 4 D square whole square. So it is FL by 2G pi by 4 whole square into D to the power of 5 into Q square. This is called as R. It is equal to RQ square. So kindly note that. Then fourth point, as it is difficult to solve the pipe network problems Analytically, analytically, right? We use successive approximations in the solution of the problems. That is next. The last one is the most popular method to solve the pipe network problems is Hardy cross method. This is the most popular method to solve pipe networks. Now I will explain you also what it is and then how to go about. For example, I take because this is only in the villages or towns, it may not be exactly that. Don't take all will be like rectangles, all will be like what you call it as squares. Only for explanation sake, I am taking it. For example, this is the network I will take it. Just so this is A, this is B, for example, C, this is D, for example, this is E, this is F, and this is G. Right? If you see, this is the whole network. This is how the pipelines are arranged. So the junctions means two pipes wherever they are joined. It is all called as junctions. This A, B, C, D, E, F, G are the junctions. Now, if I are the now this is the flow in, and finally this is flow out. This is the thing. So now if I take this as a diagram, now if I take it, this is here, it is like this is the direction, this is the direction which is given, because these are all flow directions which are given. I am not doing anything in this. Any problem when you are doing from the source, from the starting point to the end, how the flow takes place, the direction we should be knowing it. This is how actually the flow is taking place in the thing. So this A, B, C, F is one loop actually. Similarly, G, E, F is another loop. G, E, H is another loop. G, H, D is another loop. G, D, C is another loop. Like that, there are many loops in this particular problem actually. So again, he mentioned that the flow into the junction is equal to the flow out of the junction. That is the first point which I mentioned for. Then algebraic sum of the head losses in any loop should be zero. Suppose this is clockwise, this is clockwise, this is anti-clockwise in the GC. Suppose again this is actually in the anti-clockwise, and again this is. So now if I take it in this loop, this is clockwise, AF is clockwise, the head loss in AF is clockwise, the head loss in FG is clockwise, whereas the all other three are anti-clockwise. So the summation of all these head losses must be equal to zero. That is that. And head loss in any of the things is equal to just FLV squared by 2GD. So instead of writing in terms of V, I am writing it in terms of Q because I know the diameter already. So in terms of Q, I am writing it. So that is why FL into FL by 2GD into Q square by pi by 4 D square whole square. So if I take it FL by 2GD 2G into pi by 4 whole square, that all one constant if you bring it out. On the other side, it is Q square by D to the power of 5. So this all if you take it as one, the total, that will be RQ square. That's what I mentioned in the previous all four. And to solve this problem of networks, there is no straight cut analytical method. So you need to do successive approximations. Slowly start doing one after the other. then finally you end up the right solution. That is the next one. How that successive approximations are made, the best method for that successive approximations is the Hardy cross method. So now we are only discussing about what is that Hardy cross method. In this Hardy cross method, how we go about the problem. Only now at this level only I am talking about the method, right? What is the our problem actually? Discharge in each of these pipelines, how much, how you are going to distribute. For example, here x discharge is available, so this x discharge, how you are distributing into the pipe network, how what is the amount of water that you are sending. For example, here 100 meter cube per second is coming, how much is going into the AF, how much is going into AB, that right. For example, by the time here comes, it comes, suppose you are distributing 50-50. Now here 50 is coming, are you, how this 50 will go like this, then from this 50 whatever it is, how much will go into this line, how much will go into this line, like that at each junction, or which we call it as a node, then we need to really decide, and deciding that discharge in each of the pipeline is the method actually. What is the amount q in each of these pipelines is our question actually. How to determine that is our question. First, that what we will do, number one, what, how we will start basically in this method. First, in a trial distribution of discharge is made arbitrarily such that continuity equation is satisfied. What do you mean by that? Now I am telling, I know what is the flow in, that means how much is the flow coming into the network, I know. This will be given to you. But how that is distributed is the question. So now what, I don't know anything. So what I, for example, based on experience, what I will do, depending how many pipes this particular AF is supplying and how many pipes this AB is supplying, that I will see. And for example, I assume that in this AF pipeline, out of 100 meter cube per second, which is given to me, then suppose for example, 60 is going in AF and AB 40, because remaining is only 40, because continuity equation is to be satisfied. So if I assume 60 meter cube per, this is only arbitrarily, there is no rule for it. Start with some value first. That is the on question I am giving it. Suppose if I say here 60, naturally this should be 40. So that, like that, if suppose you are taking this as 70, this will be 30. If you are taking 80, 20. If you are taking 50, 50. Like that, arbitrarily, first discharge thing, you choose it. Such that what is the condition for you? You is the continuity equation is satisfied at each of the node. That means, for example, 100 you are giving, 60, 40 are coming. So now 40 has come. So there is nothing. So all 40 will go. Once 40 comes here, how much should go to here? How much? So naturally 40 means incoming is 40. So outgoing, for example, this is 30, this is 10. So like that, this continuity equation is satisfied at each node. That is what I mean by first step. Then second, with this trial value, with this trial value of discharge, find the head loss in each pipe. So now first thing you have done is whatever discharge given to you have distributed to each of the pipe basically. Once you have distributed that, with that discharge value, whatever trial value, the trial value of discharge you take it, then calculate what is HF is equal to R into Q square. What is R actually? R is equal to, this is F L divided by 2G pi by 4 whole square into D to the power of 5. Friction factor of the pipe is known to you. Length of the pipe is known to you. Diameter of the pipe is known to you. So you can calculate this R value. Don't think it is specific weight, it is R value, just some R value. Then now put that R value here, and already you have given some trial value for Q, so calculate HF. This is the second step. Once HF is calculated, now third point is take any loop, take a loop and find algebraic sum of the head loss. See it. So already I mentioned here clockwise head loss is positive. Anti-clockwise head loss is negative. So like that, calculate the algebraic. Suppose if algebraic sum, basically if you do it, then what will happen basically if you calculate, if the net head loss in each loop is 0, then the discharge you have assumed is correct, but it will not happen. Then correction to discharge has to be applied. You have to apply correction for the discharge. After applying correction, again calculate head loss in each pipe, and find the net head loss in each loop, and continue this process till net head loss in each loop is 0. At that time, whatever discharges you have taken are the correct discharges. So this is the topic, and I will give you the correction factor also. Just I will give you for the sake of just noting down what is the finally people will apply, what is the correction factor and how they will apply. The correction factor I will share with you in the classroom also. Just this is the general method actually solving the RD cross method basically for solving the pipe network problems. Right here, I will stop this lecture and we will take up next in the next lecture with continuation to this. Thank you. So in this particular class, we discussed about what is a pipe network problem and what is the thing that which we have to find out distribution of flow in each of the pipes of the pipe network, and for that what method is used, what is the general solving procedure for that method. These aspects we have learned, and we will take up the in the next class the correction factor that has to be applied in these particular pipe networks and proceed further. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.